Welcome to this video on the architectural blueprint of mathematics, set theory. We will explore the fundamental structure of sets, their operations, and the universal logic that governs them. Georg Cantor, the architect of the infinite, developed set theory to solve complex mathematical problems. His work serves as the foundation for modern mathematics, defining a set as a well-defined collection of objects. In set theory, we use specific syntax. Capital letters represent sets, while lowercase letters represent elements. We use the epsilon symbol to denote membership, as seen in these standard numerical sets. Sets can be represented in two ways: roster form, which lists the elements, or set builder form, which uses a rule to define them. Remember, in sets, order does not matter, and elements are not repeated. Sets vary in magnitude. There is the empty set, which contains no elements; finite sets, which have a definite number of members; and infinite sets, where the number of elements is not finite. Two sets are considered equal if they contain exactly the same elements. By stripping away concerns for order or repetition, we can determine the structural equivalency of different set representations. Subsets represent a nested architecture. A set A is a subset of B if every element of A is also in B. This creates a logical chain, such as how natural numbers are a subset of integers, which are then a subset of rational numbers. Intervals of real numbers are continuous subsets. These are defined by their boundaries, which can be either open or closed, depending on whether the endpoints themselves are included in the set. The universal set represents the entire context under discussion, containing all potential elements. Venn diagrams use closed curves within this universal space to visually map out subset relationships. The union of two sets, denoted as A union B, combines all elements found in either set or both. This operation follows specific algebraic properties, including commutative and associative laws. Conversely, the intersection of sets A and B includes only the elements common to both. If two sets have no common elements, their intersection is the empty set, and they are called disjoint. The difference of sets, A minus B, identifies elements that belong to A but not to B. Together with intersection, these operations allow us to partition sets into distinct, non-overlapping regions. The complement of a set represents the inverse state, all elements in the universal set that are not in A. This operation highlights the relationship between a set and its surroundings. De Morgan's laws provide a synthesis, showing how set operations and their complements interact. These laws demonstrate the structural symmetry between the union and intersection of inverted states. This concludes our overview. We have covered the fundamental definitions, hierarchies, operations, and the logical laws that consolidate the vast and structural blueprint of set theory.